properties part that we were doing last time, that is OLS estimates, if we follow the assumptions, have these properties. These are the blue properties, and because of these blue properties, these OLS estimates generally we are using. And mostly in the regression analysis, most of the researchers use this OLS method to estimate, to find the estimates of the sample regression function because of these properties. And we started last time this with these properties. Last time I covered linearity and unbiasedness, specifically for the slope coefficient, and I explained you that by the same process you can do for the intercept coefficient. So today, first, just remind back that where we were at the last time. First, we started with the estimate of this beta 1 hat and beta 2 hat with OLS method, and I explained you that if all the assumptions of OLS method will fulfill, then there are properties of these OLS estimates which make them useful to use for sample regression functions. And these properties we have to understand, because all the reason behind using this OLS method is based upon these properties. And while we study the problems in the basic econometrics with the assumptions, there are things with those problems that these properties either they are not possible to fulfill, or there might be some problems with these properties if all these assumptions will not fulfill. So that's the second part we will do in the basic econometrics. But first, let's understand these properties. So last time we studied this linearity and unbiasedness for slope coefficient. And I started with the variance also, because the last property, which efficient estimator, which means minimum variance, there we need a variance of these estimates. So last time I did a derivation of beta 2 hat variance. So these are the variance values. This one we did last time, variance of beta 2 hat, this derivation. This derivation we already done by matrix method also. Last time we did this variance to beta 2 hat variance. Today we will first find value of variance for beta 1 hat, and then this property, minimum variance. So linearity we did last time, unbiasedness that I'm trying to explain last time, and we first did it with the slope coefficient. Today let's do it with the intercept coefficient first. This was the variance of beta 2 hat that we derived last time. Next is the variance for the beta 1 hat or the beta naught if we are taking it from the Cotsianis. So first, similarly for the this beta 0 hat, this intercept coefficient. First, let's prove it that it is again, it's also an unbiased estimate, and then variance of this particular beta 0 beta 1 hat, which is intercept coefficient. And then let's see how these variances are efficient or minimum variance, this particular property of the OLS estimates. From the derivations, we know that beta 1 hat or beta 0 hat is equal to y mean minus beta 1 hat x mean. This we already did in the derivation part, right? This one. This we initially in the OLS estimates, we already estimated. So using this particular equation, now let's first prove that this beta 1 hat is also unbiased estimate, and let's find its variance. Now, in the derivation of variance, we use this notation, right? Or in the unbiased property that beta 1 hat is equal to summation ki yi. Actually, this yi is capital. It's not small y. It's a capital yi. Is from this particular derivation from where we started it. This beta 1 hat slope coefficient, right? From here we started it. That this is equivalent to this equation, and we can write this x upon summation xi square as ki. So this is the beta 1 hat or beta 2 hat. So let's put this value in this particular value of beta 1 hat or beta 0. If you put this, I'm taking these notations beta 0 and beta 1 hat of the chord Chinese. This is small beta 0, beta 1. In Gujarati, it's beta 1 hat and beta 2, capital beta 1. That's the only difference, but these notations you can change. If you put this particular value here, again, here it's a capital Y, it's not a small y. Now, if you take, if you open this particular or change it in this particular format, y mean is equal to summation y upon n. Deliberately, we are using this value here. Then constant is outside the summation, and then ki yi. So we can write this beta 0 hat as just take yi common out of this particular bracket. So it will remain 1 by n and minus mean ki. So this is we are taking this particular value because we have to prove that this particular sample estimate, the expected value of this sample estimate, this beta 0 hat, is equal to the true population parameter. This unbiased property we have to prove. So from where this particular population parameter will come in picture? So that's only come from your actual population yi value. That's why deliberately we are using these equations. In the beta 2 hat also we use this particular equation because only when we put this yi value here, then only we can have this particular value of population beta 1. That's why we are using this particular notation. So deliberately we are changing to this particular form. Now if we take expectation and put these values, so yi is equal to beta 0 plus beta 1 xi. So just put its value, expected yi value. Now this is a constant because this ki is xi upon summation xi square, and as we know that xi is fixed in the repeated sampling, that's a non-stochastic term. So that's why we can keep it out of the expectation. So now it's expected yi, we can put its value. It's not absolute y. I mean, if it's absolute y, then there's definitely error term here also, but it's a expected yi. So expected, in expected y, there is no random term, right? Expected y is regression line points. Just put these this particular value here. Now multiply first beta 0 upon n x mean ki with beta 0, then with beta 1 xi, beta 1 xi. Now, as we proved this in the derivation of beta 2 hat or beta 1 hat, that summation ki is 0 and summation ki xi is equal to 1. So if you put these values here, if you need these proofs that we did last time in the derivation of beta 1 hat, so just go to that part, and there we have proved that it is equal to 0 and it is equivalent to 1. So if you put these values here, now this term will be a 0, so it will be cancel. It will cancel out. So we will remain with the this particular term, and we can write it xi upon n as summation xi upon n as mean. And here it's this summation ki xi is 1, the remaining part is beta 1 x mean. So it will cancel out. So we will remain with the beta 0 only. So it means expected value of beta 0 hat is equal to beta 0. But graphically it means last time we did it that unbiased. It means that if you have n number of samples and you can estimate its intercept coefficient beta 1 hat, sorry, beta 0 hat, you take that average of all those sample estimates that is equivalent to the population parameter. It's not that your individual samples estimates are equal to the populations. That's not possible because might be because of sampling error or by chance. But if you take an average of all those sample estimates, that's equivalent to your population parameter. So that unbiased that it means. The next we have to prove that minimum variance, that it's not only that it's unbiased, but it's also if we have estimates from any other method, not from the OLS method, but from any other method, compared to those methods, the variance of OLS estimate is less. So it we say it as a minimum variance, efficient estimators. So that's the last property of this blue properties or Gauss-Markov theorem that we have to prove. So we need a variance for that. Last time we did the derivation for the beta 2 hat. Now for the beta 2 hat, or if it's a small than beta 1 hat, today we need again it for the intercept coefficients. Now to find the variance of this intercept coefficient, then we need a formula of variance. This is the variance formula in form of probability. So we already proved that expected uh, beta 0 hat is equal to beta 0. So we can just put here. And this particular, this right hand side is the final answer. So before that, just now we have to solve it. In the last equation, we have this value that beta hat minus beta 0. If you go by this Gujarati method, then you have to put this value here that beta 0 hat minus beta 0 is equivalent to the residual term that will appear here, like we did in the this Gujarati part, like in the beta 2 slope coefficient. One is this is the one method. Another method we can use the Courtsanis method that I explained to you last time in case of slope coefficient. Today I'm going with this Courtsanis method. Just put here values in form of expectation. So variance of beta 1 beta 0 hat. Here just put the value of beta 0. That is the Courtsanis method. You can use both the methods, answer will remain same. Just put its value. Its value is, as we did in the last time, that summation 1 upon n minus mean ki as yi from this particular equation, from here. Although we started with this particular equation, but we converted deliberately here. So just use this particular equation, put it in the with the variance. So variance is square of this term, this variance generated in the square form. So it's there are two terms here. First one is this one and second one is this one, variance of yi. So variance of yi, as we used in the last time, is equal to the variance of residual terms. And if you need its proof, I think last time also I explained you that the variance of yi is equal to this particular variance of residual terms. Just see this proof how this is equivalent to this particular value. because Accordshan is using this particular notation. So if you need a variance of yi, so you have to take yi minus expected value of yi, and expected value of yi is beta 0 plus beta 1 xi. So if you just put this value here, expected yi, this expected value of residual term is 0 by assumption. That we also proved it in the numerical properties. So we will remain with this particular value, beta 0 plus beta 1 xi. So if we take its expectation, the expectation of constant is constant, and since xi is again fixed in a repeated sampling, so this is again count as a constant. So expected value of yi will be beta 0 plus beta 1 xi. So if we use this particular value, if we substitute this particular value, now this will be the equation. Yi is beta 0 plus beta 1 xi plus residual term, and expected yi is beta 0 plus beta 1 xi. And if we take its negative sign, so this will be the variance of the yi. So this is this will be cancelled out. These two terms will cancel out, so we will remain with the expected value of residual squares, and that we have assumed that this is a constant term, homostasticity assumption. So variance of yi will be variance of residual term. So if this is the case, then and we can put this particular value here. The variance of yi is sigma square. The remaining part is 1 by n. This is whole term. Square, just take it square. A square plus b square plus 2ab. Now put xi value, sorry, ki value. So as you prove that summation ki is square, sorry, ki is equal to 0 and summation ki square is equal to 1 by summation xi square. This we proved last time in the beta 2 had derivation. If anyone of you have doubt, then you can ask it. Just revise that derivation. There we have proved it. Just put a value of this ki, that is xi upon summation xi square, and just take its square, we'll get this particular value. Now variance of beta 0 hat is sigma square. This particular value come for the variance of yi and the remaining part, 1 by n square minus this particular term. So how this particular term will be remain with this term. If anyone of you have doubt, you can just ask here that how this particular value will be now remain with only this particular value. It's just we have solved this particular equation. If you solve this particular equation, you will get this particular equation. Just you have to put this value that ki square is 1 by summation xi square, and this particular equation, that is 2 mean ki, and you will remain with this particular, or just let me sort it for you if you want. Any doubts so far? Yeah, I understand means these steps you have to practice. There might be many doubts, but in any case, whenever you have a doubt, you can just ask me in Skype anytime. In any step, just take its snapshot and put on with the question mark in the Skype that I'm facing this particular problem in this particular step. Or if you're not facing, then it's okay. Okay, let me do it. Okay, so I'm saying that this particular term is equal to this term. So for that you have to solve this particular term. Okay, the original term is 1 by n square minus in a bracket 2 mean ki upon n plus mean square and ki square. A square plus b square minus 2ab. So if you can just put these values here. Ki is xi upon summation xi square. And here you can, as we prove that this is 1 upon summation xi square, this particular term that we proved in the last time. If you can take can solve these two terms, and we will remain with the, let me see if we have to prove this, 1 by n one by n plus mean square upon summation xi square. So this is, we have to prove this particular equation. So just solve this particular part. In this particular part, if we open this summation part, there is a summation. So summation ki is 0. So even if I want not use this particular value and use as a ki, so summation ki is equal to 0. This whole term will become 0. So we remain with the n square, and other term is square upon summation xi square. Outside we have a summation. So if we put a summation here, it will be n by n square plus, it's a constant term, so it will be n summation square upon summation xi square. This n will, n and n will cancel it out, so it will be 1 by n plus mean square with n summation xi square. So this was the value here. Summation with the constant will remain same. So now you can see this particular value. Summation xi square plus n summation n mean square. If you can solve this particular equation, we will get with the only summation xi square. So this is the final formula we have, summation xi square upon n summation xi square. Any doubt in this particular variance? Although in the last time I shown you that with the matrix method, these individual derivations are not required, but still if anyone have any doubt. Any of these steps, this particular term is get 0 because of the summation ki. Here with the summation with the constant, it's n, so it by n by n square, so it by 1 by n. And this particular part, mean square, this is a capital X actually, it's not a small x. This summation ki square is 1 by summation square, so it is 1 by summation xi square, and this mean square with the n term, it's this will be here. If we take its LCM, then it will be summation xi square into n mean square by summation xi square multiplied by n. Any doubt in this particular part? Now this particular term is solved in this particular form, that this is equivalent to summation xi square is equivalent to this particular part, and if we add this particular part, it will cancel out. So in the end, we'll remain with this particular formula, sigma square summation xi square and summation small xi square. Now this is a difference with the variance of beta 1 hat, the slope is the different, and this variance of intercept is different. Any doubt? Okay. So if you see now, the variance is these two estimates. This is the slope coefficient and this is the intercept coefficient. These two variances are different. But if you go by matrix method, then as last time I have explained you that in the matrix method, it's not that individually you have to calculate, but with the matrix of this particular x transpose x inverse multiplied by variance matrix, you will get variances of all the estimates, beta 1, beta 2, beta 3, all the estimates by this simple matrix method. But to simplicity or to explain you the process of this derivation, I'm just deliberately using this bivariate method, and mostly I'm going to use with the Court-Sianis methods of derivations. Any doubts so far in the variance? Just to remind you what we are actually doing, that first we have estimated beta 1, beta 2 and all estimates from the OLS method. Now to prove blue, then we did assumptions, because these blue properties are only fulfilled or proved when assumptions will fulfill. So we did the assumptions, and for blue properties we also need variance of these estimates to prove that this is and these estimates have minimum variance. So for that we also need variance derivations. So first we did the slope coefficient. Last time that we did the variance of slope coefficient, and this was the value of the slope coefficient variance, and today we did with the intercept coefficient. So this is the variance value of intercept coefficient. So now we will remain with this third property, minimum variance. This is the third property, that efficient estimator. It means it has the minimum variance in the class of all such linear unbiased estimators, and unbiased estimator with the least variance is known as an efficient estimator. So now we have to prove this minimum variance, but before that there is one important derivation that we have to understand, and I'll tell you the reason. Just one slight mistake, I think. Yeah, here yeah, this n will not be part of here because it's already this particular value. Here this 1 by summation xi square. This particular value is already after opening the summation, because this value is of the summation ki square. So this is already the summation is opened. So n will not come here. It's just 1 by n and mean square divided by summation xi square. Now, one important point which I want to highlight here, that in both the derivations, even if it's beta 1 hat, or that was the slope coefficient, or even if it's intercept coefficient, we use this particular derivation here, that variance of yi is equal to sigma square. And where this proof is given, means this particular proof in the derivations, or even or if you can go by this Gujarati method, they have this use that this expected of ui residual square is sigma square, means this is a constant, that's homoscedasticity assumption that we have taken. Let me show you that assumption, this particular assumption, that variance of ui will remain constant, and variance of yi we also proved that is equal to variance of this particular residual term. It's depend upon the residual variance of residual, and we are assuming that it's a constant. So we are using it in both the derivations of variance of beta 1 or beta 2 hat. Now the question is that your variance of beta 2 hat is from the sample, right? It's a sample estimate. But the notation sigma square which we are using here is from the population parameter. So it needs that you might get confused here, or at least you have to ask this question, that why we using here population variance for the sample estimate. This homoscedasticity is okay, but it might be a homoscedasticity. While we are doing these assumptions, it is not specific to the sample regression function. These assumptions are generally for the regression function. So here it's not the question whether it's a sample or the population, but while we do these estimates, we work with the sample estimates. So we have only sample data. So here we are using here the population variance here. It's not a sigma hat square, means it's residuals variance. It's a population variance which we are using here in both beta 2 hat and beta 1 hat. Even if it's a beta 0 hat, here again in the variance we have used it, sigma u square, and we have saying that the variance of yi is sigma u residual square. But is it that sample variance of residual is equal to the population variance? Is not. So similarly, like we did the unbiased, like sample estimates is equal to the population parameter. Similarly, we have to prove that the variance of residuals or the expected value of all the variance residuals of the sample is equal to the population variance of residual. That proof we have to prove because that indirectly we are using here. This particular, like if we go by this Chinese method, they are using this variance of yi is expected yi minus expected yi value, and this yi minus expected yi is what? This is residual, right? Means if we have this equation, population equation, this particular equation, beta 0 plus beta 1 xi plus residual. This is the estimated part, right? This intercept and slope estimate. This is the estimated part. So expected yi is beta 0 plus the all the regression line points. So if we take a subtraction, this yi minus expected yi. So this is yi this equation minus expected by this equation. So we will remain with the residual term only. And we are saying that this particular expected of the residual square is equal to means the variance of the residuals and if expected value of variance of the residuals of samples is equal to the population variance. Here it's only in the population, there is no hat here, means this proof is in the form of population regression function. But in generally, if it's a sample residuals, if we take a variance of all the samples of residuals, its expected value is equal to the population variance. So this is we are using again and again that wherever we have this particular term, we are using this sigma square homogeneity assumption as well as variance of the population parameter. So we have to prove that it is equivalent to the population parameter. I hope you are getting this question. Let me give you this particular proof. This is only, I think, today or maybe tomorrow. The last part I'm taking the derivations. Then I have to go come back to the applied part with the Stata software. But before that, it's important to understand because in all the coming problems, the next part, this multicollinearity, heteroscedastic autocorrelation, all the consequences are interlinked with these blue properties. So this is not that this is only for the derivation part. No. All the OLS problems with the assumptions are interlinked with these blue properties. So that's why it's important to understand these blue properties because all the consequences are related to these blue properties. Okay, let me explain it again. That what I'm talking is that the variance of the like we have this data of y, right, x, the variables we have. Then to find the regression line, means the relation between this x and y, we estimated a regression line, right? That regression line is beta 0 hat plus beta 1 hat and xi. This is our expected value of y, right? This is expected value of y given the xi. Or you can say y hat. And our residual term is yi minus this expected value of y. That is our residual term of sample. So if you take a variance of this particular residual sample. This is same like the variance we do in the or if you're taking a it's ui square if you are taking u hat square if you're taking samples notation. This is the same variance formula. Like if you have a x variable, if we calculate the variance, how we calculate? We take x minus x mean, right? We take its square and divide with n minus 1 if it's a sample, otherwise n. That's the variance formula, right? Here in place of this x minus x mean, it's already a u hat, and this u hat is actually y minus expected value of y, right? Or you can say y minus y hat, right? This is the residual term here we have. And if we take its square and divide by n minus 2, that's the variance of this residual term. Why 2? Because while calculating this residual, we already calculated two parameters, beta 0 hat and beta 1. So there is a loss of 2 degrees of freedom. So it's n minus 2 degree of freedom, n minus 2 degree of freedom. So this is the variance formula, but as we have using at many places that expected value of residual equal to constant variance. This variance is not of the, we are not using the variance of sample here. In all the assumptions, we are using variance of population parameter. So we need it, this, we have to prove this, that expected this particular variance of the samples is equal to true variance of population parameter. Although we are using it at many places, but we didn't did its proof that how it is equivalent to this particular means. Theoretically, what it means that if you have a 10 samples, you take a variance of residual of your samples, which is also a variance of y, right? Is, and if you take its average, that's equivalent to the total variance of the residual of population or variance of your y in the population. So that we are using here, but we have to prove this. So this particular proof we do in graduates and master courses in econometrics. So might be those of you want to interested in that particular derivation, so that I am doing this particular derivation before jumping to the minimum variance part. So anyone, any doubt here in that what this derivation means, that this proof we have to prove because we used it, right? If you can see here in the beta 1, here in variance of yi is equal to, we have used this particular value, right? Similarly, in case of beta 1 hat also, variance of yi, we have used this particular value. And as I told you that in the Cotisanis, they have proved that this variance of yi is equal to this particular term. And we didn't did any proof for this. We are assuming it. So we have to first prove this particular thing. So this is equivalent to this term. Variance of yi or variance of the residual term of the sample is equal to the true population parameter, but not for all the samples. But if we take an average of all the samples residual variances, that is equivalent to the population residual variance. This proof I'm going to do. Okay, so variance of the random variable residual which we are taking. Now this is the variance formula, right? As I explained you that in simple variance, we have a summation x minus x mean, its square and divide by n minus 1. Similarly, if we have a residual term, its square, its summation, and divide by n minus 2. Now I told you why this is, what is this residual term is. This residual term is yi minus expected y. That's in form of this descriptive stat. You can understand it that this is x minus x mean, like x y minus expected value y. That's the same thing. Only here it's in the probability term. Now we have to prove that if we take a average of all these variances of all the possible samples, that is equivalent to the population variance, because we are using in all the derivation, you have to see that we are using sigma square. That is for the population, not for the, because if it's a sample, it's a sigma hat square. But everywhere you have used in all the derivations, you can see in this all the derivation, it's a sigma square. Even it's a matrix form, you can see here it's a sigma square. It's a population variance. Similarly, in the beta one, it's a sigma square. Same we did for the slope coefficient, sigma square. So we have to prove that this is equivalent. That's why we are using it. So this is the residual term. You can use UI or EI, whatever you want. Let's suppose we are taking it from the sample. So actual Y minus estimated Y value is that gap is the residual. Let's take it a gap for the sample as a EI. So variance of residual is, now here notations you have to note means either you can use UI or UI hat, or like in here in the code science, what they have done is that they have used sorry, yes, UI and EI means for sample they have used this particular notation, and for population they have used this particular notation. So in place of EI you can just write UI hat. Yes, that's the only difference here. So what will be the variance? Is the variance formula. So as we know from the assumption that expected value of residual is 0, so we will remain with the expected value of residual square. And that's what I'm saying, that in all the places in these derivations, we have used that expected value of UI square is equal to sigma square. So that proof we have to prove. Now, this is the residual, right? Yi minus y hat. Let's take it in the deviation form. Just try to understand this red part. This is the equation, like population regression function. Just take summation on both the sides. Tree, okay. Summation both the sides, it's constant, that's why multiply by n. Now divide both the sides by n. You will get this equation. Y mean equal to beta 0 plus beta 1 x mean plus mean of residue. Now just subtract this equation from the original first equation. Now we have yi minus y mean, beta 0 minus beta 0 plus beta 1 xi minus beta 1 x mean, and ui minus u mean. Now you can write this equation in deviation form. So deviation form, it's small yi equal to beta 1 xi. This will cancel out, and ui minus u mean. This is the deviation form. So this deviation form here we are going to use deliberately, because for this proof this equation is required. Don't worry, means in all these derivations it's not that you have to always you have to remember these derivations when you apply the regression. No, the end results you have to remember, and you have to keep in mind that how your end results will change if any of the assumptions will violate. Means that's the purpose here. These derivations I am taking in detail because might be one is just watching these videos for their exam purposes. They might have these derivations in their syllabus, so that's why I'm explaining. But only the purpose here is that you have to understand for this derivation, the purpose only is that understand that the expected value of, if you want to take it in UI form, is equal to population variance. It's the U hat square, and it's variance of U hat square, as we know that this, or if it's taking Kotsian is taking its EI form, is equal to this particular population variance. So that proof we have to prove. Now, from this particular deviation form, now we can say that y hat is equal to beta 1 x, beta 1 hat xi, because when we have expected value of y, so expected value of u is 0, so we will only remain with this particular value. So our residual term is equal to x, ei is equal to beta 1 xi plus minus. What this means is that this particular equation is, this is residual, right? This is a residual. Residual is yi minus y hat, right? This is y hat from here, and this is yi, this particular term from here, and residual term is yi minus y hat. Here we are doing it in a deviation form. That's why equation is different. Otherwise, as we did in the variance derivations and unbiased, that equation is different. But here it's deliberately it needs in form of deviation form. Any doubt so far? This is yi minus y hat, this particular residual. You need this residual. Why? Because you have to prove that its variance is expected value of sample variance is equal to of the residual is equal to the residual variance of the population. That's why we need it in form of residual. So you can now take summation square. Why this summation now and square? Just see the variance formula. This particular formula. This is the variance formula for the sample residual. Summation ei square by n minus 2. So we need value of this summation ei square. So this summation ei square is to get this particular value, we solve this whole equation. So this is ei. If we take its square and summation, that is summation ei. It's a numerator value of the this residual square. Any doubt? If you do it in the Gujarati notational form, that is this residual square of the sample is equal to summation ui hat square upon n minus 2. So in place of ui hat, this Kotsian is using ei. So these are the same things, okay? So don't get confused with it. And in place of this, it is expected value of ei square, right? From the variance formula, this particular variance formula. this formula. If it's you are doing with the Gujarati, then it's just it change is that in place of a, then it's expected ui minus expected ui hat. It's clear if you're doing for the sample, okay? And this particular term is equal to 0. So that's only the change in the notations. So don't get confused with that. Just try to understand that what we have to calculate is variance of the residual, right? And that is summation u hat square divided by n minus 2. So we need a numerator term, summation ei square or summation u hat square. So that is this particular equation. From where we get this equation? That is yi minus yi hat. That is our residual term in deviation form. So if you can sort out this equation, you can write it in this particular form. Ui minus u mean minus this beta 1 hat xi and plus beta 1 xi. So this is square and summation. So this is the numerator term we have of the variance of residual square. So anyhow, not only for the this proof that sample variance of residual is average of the sample variance of residual is equivalent to the population variance of residual, means also we also need this variance of residual term, right? Because in our both the formulas of this beta 2 hat and beta 1, you can see that x for x data we have, right? We can take just deviation, its square and summation. But this sigma square value we need, right? To get a value of variance of beta 2, we need this sigma square. So for that also we need this derivation. That what will be the value of this sigma square? So sigma square is for the population, but in sample data we have the variance of the residual from the sample only. So we have to prove that this is equivalent to sigma square. That's why we are using their sigma square. But that value will come from this particular residual, right? Because population actual data for population residual we don't have. We are only going to use this particular value in place of sigma square. So that's proof we are doing, and by that we are also doing here the value of residuals, variance of this residual, sample residual. So just this particular now, just take expectation on both the sides. This equation, expectation on both the sides. Now why expectation? Because what we are going to prove is that the sample variance, it's expected, is equal to true population variance. And this variance, individual variance of sample is equal to summation u hat square upon n minus 2. Here in Code-Chinese notation, it's in place of ui hat square, they are using ei square upon n minus 2. So first we have calculated this value, right? Now because we have to prove that this expected of this whole term is equal to this, so we just ignore n minus 2 for the time being, and we need expected value that we have to prove equivalent to this value. So just take expectation here in both the sides. So if you can open this expectation, now we have a three different terms. This first one, second one, and the third one. Now these three different terms we have to solve one by one. Any doubt so far? Means in the question that what exactly we are doing and why we are doing. It's why we are doing this derivation, but it means if simply I can say that Since we did this variance of beta 1 hat and beta 2 hat, so here we use sigma square. So we need this value, right? So we also need this derivation, but we work with the sample data. So in sample, we have this sample variance, right? So how we can use this population variance? So for that, we have to first prove that this average of the sample variance is equal to the population variance of residual. So for that, for this both the purposes, to get this residual variance as well as to prove that this is equivalent to population variance, we need this derivation. Everyone is getting this point? Or any doubt in these equations? Gagan or Lavanya or Soumya? Any doubt so far? In this derivation, where we are going to prove this, that this sample variance is, its average of sample variance is equivalent to population variance. Is any doubt so far till this particular equation? You have this recorded session, so later on you can practice this one by one. But still, if you have doubt in any of these parts, you can just ask me. Okay, so to get this proof, now we have to get derivation for these three parts one by one. So first, I'm starting with this first part. That is expectation, and within that summation ui minus u mean bracket close square. Just open this square root a square, but it's a plus sign. It's not minus, otherwise it will not cancel out. A square plus b square minus 2ab. So open the summation. Summation with constant is n, and here it will multiply. Now u mean, I have used it deliberately as summation ui upon n, right? And then just multiply and division by n. Any doubts so far here? Anyone? Then it's 2, so just one cancel it out, and we will left with this part, summation ui square minus mean into summation ui, because we can also write this mean as summation ui ni, so one n will cancel it out, we will remaining with this part, summation ui square minus mean of residual summation ui. Now here in place of mean, just write summation ui upon n. So it's a square, and if we take expectation, that's only with the this residual random term. Any doubt so far till this particular term? Now this term we are always using is equal to this term, right? This is the now in the form of population. This is equivalent to this particular variance of population. This is equal to, this variance formula is expected ui minus expected ui square, right? This is equal to 0, so this is expected ui square. So expected ui square we can write as sigma square, right? This particular value. Then 1 minus n, sorry, 1 upon n. And just if you open this term, what it means, summation u hat square, is that summation of all the individual values. And if you open it again, that this is a square of all the individual values plus their 2ab, 2ba, 2ca, that for process I explained in the variance of beta 2 hat. And this particular term, by assumption, we have this assumption of autocorrelation, no autocorrelation. So this is equivalent to 0, so it will cancel out. So we'll remain with this equation only, this part of the equation. And again, this expectation of ui square is, as we did here, sigma u square variance. That is the variance of residual term. So we can write it as sigma square. So it is n sigma square minus 1 by n sigma square minus 2. This particular term will be 0. So we will remain with this equation. This is sigma square of residual and n minus 1. So this is the first part, A part. This value is for the A part. So you can see in the, because we have to prove is this particular proof. Left hand side, we are going with the sample residual, and right hand side, we are going with the population. So in this Kotsianis, they used it UI for the population part and EI for the sample residual part. So in the left hand side, we are going with the sample residuals because we have to prove this. And in the right hand, we are using the population regression, population residual. There are so many minor points in these derivations. Means if I can take this 2 or 3 times, every time we will get some new points. That's why I'm saying while you are practicing, you're getting any difficulty at any point, just ask me that. Okay, so this is the value for the first part, A part. Then we have a B part, that is expected beta 1 hat minus beta 1 square summation xi square. Now let's solve this particular part. Just take a summation xi, that is because fixed in the repeated sampling, out of the expectation. So expectation beta 1 hat minus beta 1 square, that is variance of beta 1, and variance of beta 1, as we proved in the derivation, is equal to sigma square 1 minus summation xi square. So if we put this, this will cancel out, so we will remaining with the sigma u square. That is the second part. And third part, just let it keep 2 part out of this, and the other remaining part. Now beta 1 hat is equal to that, this particular term we are using in all the variance derivations. So beta 1 hat minus beta 1 is equal to summation ki ui. This particular equation is from the unbiased part. If you go back to the unbiased part, there you will get this particular equation. In the end, before taking expectation, you will get this equation. So if we put this value summation ki ui here, now if you multiply these, now here summation xi, we know it's equal to 0. So this term will cancel out, this particular term. It will remain with the summation ki ui and summation xi ui. So if we put this ki value here, which is equal to xi summation xi square. So this is xi summation xi square. It's double square and summation xi square. So again, if we elaborate this particular part, that is square of individual items plus all the 2 AB terms. So again, here you will find that we deliberately using this because we know that this is this particular term because of the assumption of expected value of these two terms is equal to 0, no autocorrelation assumption. That's why deliberately we are elaborating this equational form. Now this particular value will get 0. So here we will remain with the summation xi square summation xi square plus summation xi square and its expected value y square. This is equivalent to the variance. This will cancel out. So now if we put all these three values in the equation, so expected of this ei square, that is the sample residual, or I can say summation of ui hat square is equal to this particular term. All these three values minus 2 because this third part is with the minus 2. And if we solve this, we'll get this term equivalent to n minus 2 sigma square. So if we take n minus 2 here, it's equivalent to this. So what it means is that if I can say it in form of Gujarati, that is summation ui hat square upon n minus 2, its expectation is equal to residual, or expectation residuals variances is equal to the true population variance. Resident variances of samples is equal to the population variance. So that's the proof. That's why everywhere we have where we have a expected value of this residual or variance, this variance in form of probability we can also write as expected value of ui square. Because in probability the variance formula is expected, sorry, if it's a hat, ui hat minus expected value of ui hat, that's the variance formula, and this is 0 that we put, so this it is always expected ui hat square. If it's a sample, if it's a population, then it's a ui square. So this is the variance, means this is the variance, actually individual sample variance of residual, this particular term. And in place of that, we are using everywhere this particular term because its expected value is equivalent to this particular term. That's why wherever we have this particular term in all the derivations, we have written sigma u square. So what it from where this value will come from? From this particular value. If we have this value, we can use this value in place of this value. Is it clear that why this particular derivation is important and how you have to do it? Any doubt in this derivation? And even if you have any doubt in this derivation? So now you can understand the variance of beta 1 hat and beta 2 hat. From the derivations, we have these values like this one. So wherever you have this sigma square, now you can understand that which value you have to put here. Means x data you have, but for variance now this is actually from the summation you had square of residual upon n minus 1, and on an average is those residuals are equivalent to the sigma square, so you have to use this sample variances values here. for both the variances. So now we are done with these derivations of estimates and their variances. Now just see, when you have this beta to hat, you have x and y. This data we have, so we have no problem. But when we have a variances, we have a sigma square. So we definitely need this value. But since we are working with the sample, so it's a sigma hat square means residuals, but it's proved that average of all those residual variances is equal to the population variance. So we can use those sample variances of residuals in place of this sigma square, while practically we use these values. Is it clear? Means still variance, derivation, any doubt for estimates? Then we can jump to this last part, minimum variance property. Any one of you have any doubts so far till these derivations? So maybe I think my mobile is not getting charged today, so I can take this minimum variance part tomorrow. Means now we are only left with the minimum variance, this last property. And after that, now then we will do this other part of regression, like as I told you in the beginning, that we have to complete this table and then problems. So far we have completed these estimates derivation part. Standard error is the under root of the variances. So we are also done with the variance part. These individual significance test, we know that the how we do this t test as we did in the second part as well. But again, we will do this hypothesis testing. So after this, after minimum variance property, then I'll jump to this overall significance of the model and goodness of it, R squared, that we will do tomorrow. R square and overall significance of the model. These two important parts of the regression model. And after that, only the change will be might be in the nature of variables, like here we are doing quantitative dependent variables and quantitative independent variable. It might be a qualitative dependent variable, then dummy variable models are required, or might be sometime you have a non-linear regression models. The examples I have given you, that might be a change, or the assumptions that we have taken, all the assumptions that might not be fulfilled. So you will face the problems. So that's we have to understand in detail the assumptions, multicollinearity, autocorrelation, hetero. But before that, we will do few numericals with the Stata software after all the derivations. So anyone of you, any doubts so far till these derivations? Estimates and proof, this particular proof that this sigma square is equal to the expected value of sigma u hat, sigma hat square. Now in the derivation part, we are only left with the minimum variance property part. Other derivations are done. So tomorrow after that, I'll just jump to this goodness of it first, and then overall significance of the regression model. First only with the bivariate, and then we will do it with the multivariate as well, this goodness of it and overall significance. And then we have to start with the problems of these assumptions. For that, I need 6 or 7 classes in detail for those problems, and 1 or 2 classes for the dummy variable, this dummy variable models as an independent variable. Any doubt so far, these derivations? Okay, so because my mobile is not getting charged and I am worried it might get closed. Okay, if you want in brief, I can start this minimum variance derivation. But this minimum variance or the efficient estimates meaning is that if we have a variance, sorry, estimate of these beta 1 hat or beta 2 hat from any other method except for the OLS, the variance of OLS estimate is minimum. If I can explain it with the graphical method. Yeah, this one. This last diagram. Let's suppose we have a two different slope coefficients, beta 2 hat from the OLS method and beta 2 star from any other method. The variance of beta 2 hat, which is from the OLS method, is minimum as compared to or less as compared to the any other. But its implication is that if the variance is high, like of this beta 2 hat, then there are maximum number of chances when this particular value is not nearby the true population parameter. So we need its value as minimum so that maximum time this value will be nearby the true population parameter. So minimum variance is required. Otherwise, it might be possible that maximum time its value is not nearby the population parameter. We can't use that particular value, although we have to test it with the hypothesis testing. But at least theoretically, we need a minimum variance. So that's why in the OLS, this is the property and this is useful that it has a minimum variance property. I hope you got this point that what this minimum variance means in this graphical form. Okay, so my mobile, sorry, this battery is now just 2% and electricity is not here. So tomorrow I'll first complete this minimum variance and then I'll jump to the other part, this particular, all other part of the regression models, goodness of it and overall significance. And then we will done with the regression estimates and derivations. Then we will start with the problems and other type of independent variables like qualitative variables and problems of OLS estimates. So I think this is enough for today. So we are now just on the last part of this process, the minimum variance part, and before that we also calculated the variance derivations and estimates derivation. So thank you so much. Tomorrow we'll start from the minimum variance first and then goodness of it. Thank you so much.